Here is our second lesson on gas laws, and probably the last one on the topic of density and pressure. And the second episode deals with something very particular, which is Boyle's law. If you can remember from the first video, we talked about how, the first video talked about how pressure and temperature related, in that if you increase the temperature, you increase the pressure, to hold that relationship true. Well, now we're looking at volumes and pressures associated with them. Here's an example to start with. Let's imagine we have a container. This is a plunger which goes in and out, and it contains a certain volume of gas inside. Now let's drive that plunger in, so we come out with half the volume that we started with. Now what's going to take place, what's happening inside as we drive that piston in? Okay, well, the particles inside individually are still moving at the same speed. Right, so the particles move at the same speed still. And the reason why they move at the same speed is because, if you remember, temperature is proportional to the average kinetic energy. These signs here are averages. And so therefore, we've had no change in temperature in these instances. If anything, temperature is constant. So therefore, the particles don't move any faster. So is there going to be any difference in the pressure? Well, firstly, you might think not. However, what has happened is a smaller volume. And with a smaller volume, so the particles will traverse the height width of this container much more, not quickly, but much more often. So with a smaller volume, for the same speed, you get more collisions in a given time. And more collisions in a given time relates, or suggests to you, hopefully, that you have a higher pressure. If we start off with the pressure 1, volume 1, then here, though the volume has gone down by half, so the new volume, the new pressure must have doubled. So if you reduce the volume, you increase the pressure in turn. Let's describe this mathematically. In other words, the pressure is proportional to 1 over the volume. It's inversely proportional. If I halve the pressure of the volume, I'm doubling the pressure. If I halve the pressure, I'm having to double the volume, and vice versa. Or if you prefer, we could write it as pressure equals a constant times 1 over the volume. Okay, what does that look like graphically? Because part of the experiments that we carry out to confirm this, we'll need to see what it looks like. Now, if we put here the pressure in pascals and the volume standardly in meters cubed, then because it's in inverse, it will look like a 1 over x graph. Good. Now, there are difficulties in working out whether that's 1 over x squared, 1 over x cubed. However, we have no difficulty in working out whether something is on a straight line. So whereas these points that we plot experimentally, we're not quite sure what curve they suggest, we definitely know that this would suggest a straight line. So how do we plot this in order to try and create a straight line to confirm? So this is used to confirm a relationship. Okay, well, let's rewrite. We know the equation of a straight line is y equals mx plus c. Just watch this as I bring this across. Let's have p on my y-axis, k 1 over v plus 0. So I put my p for the y in pascals, I plot 1 over v as my x. My gradient will be k, and of course there is a 0 here, so my intercept will be 0. So if I were to plot pressure against 1 over volume, I get the equation. I get a straight line if this relationship holds true. Pressure is inversely proportional to volume. Okay, how do I write this? Well, this is 1 over meters cubed is my unit. We have that. So all in all, what we're saying then is the pressure multiplied by the volume gives us a constant. I multiplied that through PV equals K. And because that constant must be the same for all temperatures, the initial pressure of a system times by the initial volume of a system should equal to the final pressure by the final volume, where we have measured in pascals, meters cubed, pascals and meters cubed. However, little proviso here is, so long as you keep the units constant on both sides, the equation will still hold. So that's okay, so long as you have the same units on both sides. If you measure this in centimeters cubed, this will have to be in centimeters cubed, and vice versa. Okay, there's the theory. Now let's try some questions. Good, here's the first one. Let's just take an example of an airbag. That's inflated. Once inflated, it has a pressure of 10 newtons per centimetre squared. Once again, it looks like an odd unit, but as long as we keep them consistent, we're okay. And it has a volume of 30,000 cubic centimetres. Now, let's imagine the head hits the airbag. The pressure will increase to 12 newtons per centimetre squared. What's the new pressure? If you think no, hit pause. Otherwise, here comes the answer. Okay, right, let's write down our relationship again. Now what we're looking for is V2. So in order to get V2, I divide through by P2 on both sides. Okay, let's add in the values. P1 is 10 by the 30,000 divided by 12, and that gives us 25,000 cubic centimetres. Does that make sense? Well, yes. As I've hit the airbag, you've increased the pressure, which must have caused a reduction in the volume. You squeeze the airbag to make it higher pressure. Okay, example 2. Let's have a bubble underwater. Okay, let's imagine it's underwater initially, and the pressure is quite high, 1.2 atmospheres. Remember, 1 atmosphere is 10 to the 5 pascals. It also has a volume at that position of 6 cubic centimetres. Now it drifts to the surface. And we know the pressure on the surface is 1 atmosphere. What's the new volume? If you think no, hit pause. Otherwise, here comes the answer. So, let's write out the equation again, which we're starting with. We also know that if the pressure is greater initially, as the pressure reduces, so the volume must increase. So we're looking for something bigger than 6 cubic centimetres. We're looking for V2, so let's get rid of P1. So then P1 V2 over P2. And let's throw in the things. Now remember, atmosphere doesn't look like the right unit to use, but so long as we're consistent, we're okay. Initially it was 1.5 atmospheres, 6, divided by 1, that gives me 9 cubic centimetres. And that makes sense. As the pressure is reduced, so the volume has increased. Okay, what happens if I want the volume to equal 4.5 centimetres cubed? What would the pressure have to be? If you think you know, hit pause, otherwise here comes the answer. Well, let's just once again be pedantic and write down my equation. I'm looking for the second pressure, so in order I need to get rid of the second volume, so of course P2. Let's substitute in the value. So I started with, right up here, 1.5 and 6, and I'm dividing by 4.5, which gives me, hold on, I think I made a small mistake here, pressure 1, volume 1 divided by volume 2, so I'm looking at my second volume, my volume has decreased, therefore my pressure should have increased. Yes, that's right. So this is 3, so it gives me 2 atmospheres. So I need to move 2 atmospheres a slight increase in order to my volume turn to 4.5. Okay, excellent. Right, one more, just because this is all we need to talk about. So example 3, see if you can do this. Let's say I start with initial pressure of 1,500 pascals and a volume of 120 cubic centimeters, and I want to decrease, 100,000 pascals. What's my second volume equal to? I think you know, hit pause, otherwise here comes the answer. P1 V1, same as P2 V2. V2 is P1 V1 over P2, which gives us, okay, let's substitute 150,000 multiplied by 120 divided by 100,000 gives us a volume of 180 centimeters cubed. Okay, good. So remembering here, Boyle's law represents how pressure and voltage relate. They're inversely proportional. Okay, hope that made sense.